Hi, this is Alex from devstories.eu. LlamaIndex, Context-Augmented LLM Applications, Episode 2 of 14. You cannot just shove a 500-page PDF into an LLM context window and expect a precise answer. The model will lose track, hallucinate, or simply reject the payload for exceeding its limits. To make massive files useful, you have to tear them apart into tiny pieces and translate them into a mathematical format the machine can search. That process is exactly what data ingestion, documents, and nodes covers today. Think about digesting a massive HR employee handbook. The text lives in a giant PDF spanning dozens of complex chapters. The first step in a retrieval-augmented generation pipeline is the loading stage. This is where data connectors, frequently called readers, come into play. A connector takes your raw data source, whether that is a local PDF, a remote database table, or an external API response, and wraps it in a data structure called a document. People often trip up on this term. In this framework, a document does not mean a Word file or a PDF. A document is simply a generic container for any ingested data source. It holds the raw text along with some basic properties. However, a single document representing a 500-page handbook is completely useless for precise, fast searching. You must break it down. This brings us to nodes. A node is the actual atomic unit of data in LlamaIndex. It is a smaller, manageable chunk of a parent document, perhaps a single paragraph detailing the parental leave policy. When you process the HR handbook, the framework takes the massive document and slices it into thousands of nodes. Here's the key insight. Nodes do not just hold isolated text, they carry rich metadata and structural relationships. A node knows exactly which parent document it came from. It also knows which node logically precedes it and which node follows it. This linked structure is what allows the system to synthesize larger context later if a single chunk does not contain the whole answer. Once you have your data chopped into precise nodes, you move to the indexing stage. You need a robust way to find the correct node when a user later asks a question. This requires translating human language into a numerical format called an embedding. An embedding is an array of floating point numbers representing the semantic meaning of the text inside the node. You pass each node through an embedding model. The model reads the chunk and returns a high-dimensional vector. If two nodes discuss conceptually similar topics like sick leave and paid time off, their numerical vectors will sit mathematically close to each other in space. With these vectors generated, you construct an index. The index is the core structural component that organizes your nodes so they can be queried. For most applications, this index is backed by a vector store. The vector store acts as a specialized database explicitly designed to hold these mathematical representations and perform highly efficient similarity calculations over them. The logical flow is highly predictable. First, you configure a data connector to target your HR handbook. The connector reads the file and outputs a single document object. Next, a parser takes that document and splits it into an array of independent node objects. Finally, you pass that array of nodes into an index, which coordinates the creation of vector embeddings and commits them to the vector store. The entire ingestion pipeline exists to solve one fundamental limitation. Large language models cannot reliably read entire books at once, but they can instantly calculate the mathematical distance between two arrays of numbers. Translating your raw files into documents, slicing them into linked nodes, and encoding them into vector indexes is what bridges that gap. That's all for this one. Thanks for listening and keep building.